Hey Adam, we are back here at FAQ for our next episode. So, as a quick recap, last time we started on this endeavor of learning about quantum computers, but not from a theoretical sort of high level perspective, but we really want to get down to the, physics, the actual engineering, what's really going on. We've been learning about all of these concepts in math and quantum physics, but now we actually want to know what's actually happening in the lab. What are people building and how are they doing it? So last time we started on this journey by going through this list of 5 things, DiVincenzo's criteria, 5 things that you want to make sure that you have to see if the quantum computer you're building is actually usable, is workable. So last time we started with the first criterion, which, as a quick recap, is asking for a well-characterized and scalable system of qubits. We talked about these words sort of one by one in the context of trapped ion qubits. So maybe just to kick us off today, do you want to give us a brief refresher of, what we did last time for this criteria?
Sure. Thanks, Titan A. So yeah, I think where we got to last time with trapped ion quantum computers is they are very well characterized. We've known about ions for a really long time. And the scalable part, not quite yet, kind of working on it. And with superconducting quantum computers, kind of checked both of those boxes. Well characterized. These are manufactured or artificial atoms is usually what those qubits are called. And the scale still needs to improve, but it's going at a pretty big rate. So I think we kind of check the boxes off for both of those. But on the trapped ions, we're kind of still working on the scale.
Yeah. Okay. So that was a good recap of last time. So today we want to move from just what are the qubits to actually how does one go about working with them to do an actual computation. So that takes us to number 2 on DiVincenzo's list of things to check. So I'll just read it. Number 2 is the ability to initialize the state of the qubits to a simple fiducial state. Okay, I don't know about you. I do not use the word fiducial in my daily vocabulary. Maybe I should incorporate it, but what does that word mean? Maybe we should start there at the end and then walk through this.
Yeah, I don't think you need to add that to your daily vocabulary unless you really want to. I didn't know what it meant at all and had to look it up. But basically, it's about being able to have a state of comparison, like a stable, consistent state of comparison. So the way I like to kind of think about this, especially in the context of quantum computing, is just what your fiducial state might be for like a calculator. Before you start a calculation, usually you tap that clear button a whole bunch of times to get your calculator to say 0. That's the fiducial state for a calculator. So when you do a calculation, you know that you're comparing that to 0. If you just typed in like a random number that you didn't know was there and like closed your eyes, typed in a random number, and then started your addition, subtraction, etc. from that random number, the solution you get at the end is going to be a little bit less useful than if you knew that you were starting from 0. So my interpretation of this is that we basically need to initialize the qubits, know where they're at before, what state they're in before we actually start doing calculations.
Yeah, and that seems reasonable. I mean, I think that's not, maybe it's like a word I don't use every day, but the concept seems clear to me. So I like how you mentioned the number 0, because maybe just in the spirit of connecting these concepts to things people may have seen before. So, we talked about this in our last season, but when people talk about computation, it's inevitable that bits come up like zeros and ones. Computers speak in the language of zeros and ones. And so when you read about the quantum version of that, qubits, instead of just the number 0 and the number 1, now we always see like a 0 with a vertical line and this right angled bracket next to it. And so that's a ket 0, or the quantum version of a bit or qubit. So you have like ket 0 and ket 1, and then people talk about doing stuff with that. So just for the record, when we're talking about initializing qubits or bringing them to that like calculator version of 0, that's precisely that ket 0 that we might see on Wikipedia or in a textbook or something. So we know what that is mathematically. It's like a vector, blah blah blah. But what we want to talk about today is, okay, what is the physical instantiation of that symbol. Like I'm doing some stuff on paper, but like when I'm in the lab or standing in front of my, chip of trapped ions, what does it actually mean to put those in a state that's being represented by that symbol that we might see? Another analogy I like, it's like when you go to a symphony, the orchestra is up there, and before everything starts, like the strings are tuning, and it sounds like this cacophony of like mess. But everyone is doing that so that they can start at the right pitch. Like you have to do something, you have to initialize or tune your instruments so that when you begin, to make this beautiful music, you are all starting at the right point. And so, you can punch the clear button on your calculator, or you can tune your violin or your instruments so that in both cases, where you're beginning. That makes sense in life. And so it also makes sense in quantum computing. Does that sound good? Or
yeah. And speaking of sounding good, I really like that when the orchestra is tuning up, or when you kind of hear that noise of everybody starting to come together. So I really like that analogy of you have all these different instruments that are playing. You have to develop that bass, that zero, and that's a good tuning, making sure that everybody's tuned the same way so that they're all playing in harmony. So I really like that.
Exactly.
And I think since we're talking about these different states, ground state of this zero, getting everybody started in this fiducial state, we're going to start talking more about ions. We've been talking about ions for a while, since the whole theme of this discussion is trapped ion quantum computers. And I'd like to talk a little bit more about what an ion is, because in order to talk about how we can manipulate and control those ions to do useful calculations, I think we should make sure that we're on the same page about what exactly is an ion. How does that sound to you?
That sounds great. Let's go for it.
Okay, great. So in order to start to talk about ions, I want to talk a little bit about atomic models to really make sure that we're all fundamentally on the same page about what an atom is and what an ion is. And to do that, I think we can use the example of calcium, because calcium is an atom that's used in a lot of trapped ion quantum computers. It's not the only ion that can be used, but I think it's nice to have like an example to start from. So let's talk about calcium, and let's talk about the subatomic particles that make up calcium. And in the simplest way, we're not going to go too deep into quarks and things like that. But the species or the type, we could go deeper in that if you want to talk about the real fundamental particles here at Tide. But I think we'll at least start by talking about protons, neutrons, and electrons. How does that sound?
That sounds great.
Okay. All right. We'll start there. Maybe next episode we can get into quarks. So calcium, and I can show a model of what calcium looks like here. Okay, so here we have a three-dimensional model of calcium, and this is using the Bohr model. We'll talk more about that in a little bit. But we have these protons, neutrons, and electrons. So in the nucleus, or in the middle of the atom, we have these blue and red sort of spheres. Those are protons and neutrons. And the number of protons in an atom actually defines what that atom is. So calcium has an atomic number of 20. That means it has 20 protons. It also happens to have 20 neutrons in the calcium 40 state, which is what you would see on the periodic table, and is what's usually used in quantum computers, is calcium 40. You'll see that a lot. That 40 is the atomic mass, and the atomic mass is made up of protons plus neutrons. The atomic mass of a proton is 1. The atomic mass of a neutron is a little bit more than 1. And so you have 20 and 20, which makes 40. You also have these electrons that are orbiting in this Bohr model. They're orbiting in these different sort of shells outside of the nucleus. And electrons are really small, and they're way less massive than protons and electrons. It's something like, I think an electron is like 1/1800 of the mass of a proton or something like that. So you need like 1,800 electrons to equal a proton, approximately, something like that. And you have them rotating around the nucleus here. And in this particular model that you see here, this is what a lot of folks are familiar with, the Bohr model. The electrons orbit in discrete shells. And you can see here that there's like 2 electrons in most of these shells. Some of them have 4, and you can have up to 8, depending on the type of shell. And those electrons basically work to cancel out the charge of the protons. Protons are positive, electrons are negative. So electrons and protons will balance their charges out. And in many cases, the atoms end up being neutral. So in calcium, you'll have the 20 protons and you have 20 electrons. But things get a little bit more complicated than that. Those electrons fill up those shells. And once you get to the most outer shell, that's called the valence shell of electrons, or the valence orbital, sometimes that valence shell isn't all the way full, meaning it has fewer electrons than it actually can hold. And to anthropomorphize a little bit, atoms don't like that. They like to have full shells or empty shells. And so those valence electrons can actually be pretty reactive, and they can spin off of the atom, or more electrons can come in. And fill that shell up and being shared from other atoms that are around. And those that's due to chemical reactions, basically atoms coming together to form more complicated atoms and molecules, or more complicated molecules from atoms.
Which is how all of matter, like this is how everything around us
That's
works.
right. Yeah, this is chemistry. So those manipulations are chemistry. So in calcium, there are 2 electrons in that outer valence shell, but it can hold many more. But what usually happens in nature, like in our bodies, calcium is something like the 5th most common element in the human body, and it's usually found in things like our bones and our electrolytes. And in our electrolytes in our body, the form of calcium is calcium 2+, meaning that those 2 electrons on the valence shell were stripped away, because the calcium atom is actually more stable with those not there. So you have those ions. That's how that's where an example of an ion that you have in your body is that calcium 2+, because it's more stable than just the regular calcium. So I've been showing the Bohr model with those like very neat orbitals around, and that was Niels Bohr described that. I think it was like 1913. It's also talked about a lot, even in modern day in classrooms and things like that. It's usually one of the early models that are taught. But there's some problems with that model, and it can't explain some of the experimental results that have happened since 1913. Actually, in just like the 10 years following 1913, there were some experimental results that couldn't be explained by the Bohr model. So a more complex model, or a quantum model, was described. And that shows electrons functioning with wave-like properties. So instead of just these points that are kind of moving around, they're described as waves, and they are described as existing around the atom in different probabilities, a different probability of being able to find that electron in one spot versus another spot. And those probabilities are consistent, so we can define them, but they can kind of look like a cloud when you put them all together around the atom. So it's kind of nice to be able to think about them as a cloud of electrons around the nucleus, versus these sort of planetary systems orbiting the nucleus of a sun. Yeah. And I can show a little bit about what do those orbitals look like. So I'll show that example here. And those orbitals, now called orbitals instead of shells, you can kind of think about them as standing waves. So here, I'll show a picture. And they actually kind of look like balloon animals or something here. Look at these p orbitals. Yeah. And they have names like S and P and D and F and even H, and goes up from there. And electrons will fit into these orbitals, and they exist in this sort of probability area of a standing wave around the nucleus. So you might be thinking, okay, what's a standing wave? So there's a couple of different ways that I like to think about this, but a standing wave is basically a wave that oscillates just up and down. So the amplitude flips straight up and down, and it doesn't propagate like through a medium. Like if you think about an ocean wave, it's sort of moving through the ocean. A standing wave is just moving up and down. So one way to think about that is like a jump rope. If you have if you're kind of moving a jump rope up and down, it kind of forms that oscillating wave of the amplitudes just moving straight up and down, but not moving across the actual rope. And another way to think about this is to think about a string on like a guitar that gets plucked. And I actually have not a guitar, but I have a bass ukulele, which I sometimes play around with in front of me here. And I can pluck one of these strings, and you should be able to see it's just kind of bouncing up and down.
Yeah.
And I like this because it's kind of, we were talking about instruments earlier.
Yeah.
So you can kind of think about this vibration or wave, standing wave around the nucleus of an atom. And within the amplitude of the wave on either side of the atom is where the electron will be found with some amount of probability. So that's the more modern interpretation of an atomic model, and that helps really explain a lot of the experimental results that we see within when we're doing experiments on atoms. Still not perfect, but it's the most modern interpretation that we have at the moment. So that's about all that I want to talk about with atoms and how electrons kind of work. And I want to pull it back to calcium and talk about the formation of calcium ions and how that works. How does that sound?
Yeah. No, that's great. So let's not think of electrons as orbiting the nucleus like planets around the sun, but instead we have these sort of clouds or probability distributions around the atom that sort of says, oh, with this probability, you'll find the electron in this region. Okay, so now let's take that back to calcium. And then can you also walk us through how all of that connects back to this idea of initializing to a fiducial state? How do all of these things connect?
Yeah, that's right. So now we have a little bit of foundational information about where the electrons are. The electrons are key to all of these calculations because each of those orbitals has a different energy level. And you can move electrons across energy levels by supplying more energy in the form of a laser. And by doing that, you can move those electrons from one orbital to another, and you can assign those different orbitals as ground state and excited state, for example. So those, even you can be thinking about this a little bit in the Bohr model if it's easier to start to think about those electrons kind of moving up in those shells. But eventually it's better to sort of think about it in that probability distribution quantum model of those different orbitals instead of shells. So from S to P, D, et cetera, like these different energy levels that you may have heard of before. So I want to talk a little bit about how you can prepare a calcium an atom of calcium to be the proper ion for an ion trapped quantum computer, trapped ion quantum computer. And then we can talk about how you can actually use those valence electrons that I was talking about to monitor your state and to move into different states to be able to do a calculation.
Good. Let's do it.
Great. So yeah, first off, I know I talked about calcium 2+. That's not the type of atom or ion that's used in a trapped ion quantum computer. They use calcium 1+. So you want to have one electron in that valence orbital on the outside. And that's where all the action is going to be happening, where you're pushing that electron
the qubit,
around.
Basically.
That's the qubit. Yeah, that electron is the qubit. So in order to produce that ion, you have to do some stuff to calcium. You have to really heat it up to like something like 800 degrees centigrade. And then you hit it with a beam of electrons, and that actually rips off just one of those electrons in that valence shell. So now you have calcium plus. Instead of just regular calcium or calcium 2+ that I talked about before, now you have calcium 1+ with that electron in the outside. And then to get that into the fiducial state, it could be close, just as it is, because that is the valence electron in the valence shell. But you do this thing called optical pumping, where you can actually hit that valence electron with a special laser, and it excites it just a little bit and then brings it back down, and then excites again and brings it back down. And in that sort of bumping of up and down, that laser will get that electron into a stable ground state that is known by the engineers. There are several different states that electron can actually be in that valence orbital. And by hitting it with a specially tuned laser, you can start to filter the electrons across all of the atoms within your trapped ion quantum computer, to get those outer electrons into the proper ground state. So the laser only affects electrons in those valence shells that are not yet in the proper ground state. And if they're not in that ground state, it bumps them up a little bit, and then with some probability, they'll fall back down into the proper ground state. Once they fall into that ground state, that's it. The laser can't affect them anymore. The laser can only affect ones that aren't quite in that ground state. So that's a special sort of initialization aspect of that.
Very nice. Yes. And I think this idea of like you're supplying the electron with some energy in the form of a photon, it excites it, and then it goes back down kind of on its own. This is the spontaneous emission. It just kind of relaxes back down. Okay, so I like that explanation. There are these different energy sort of orbitals associated to the ion. And you can use lasers, which is part of the well-characterized part that we talked about last time. Like, how do you know that, sometimes the laser is sort of invisible to the ion, or when it is affected or when it's not? Like, all of this comes into the technical details and the mathematics and understanding like the inner workings of this. But okay, so these different orbitals are like the energy states. You pick one that, is sort of natural or stable for the ion. You call that the ground state. That ground state is that zero, the ket zero, the zero with the vertical line and the bar that we
Exactly.
opened.
That's right.
Yeah, okay. So you've told us how to initialize the energy level or the sort of internal state of the ion. Oh, by the way, I should say, I misspoke earlier. So earlier when you told us that we have this one electron on the valence, like this valence electron, calcium 1 plus. So I said, oh, that electron is the qubit. Let me be more careful. The electron is not the qubit. Its energy levels, the energy levels associated to the electron are the qubit. Okay, so we have two options, the ground state, and then maybe next time we'll talk about the excited state. How do you like supply it with energy so that it's in a higher energy state? That's not part of initialization. If you want to keep it there and do something with it, that's like getting into quantum gates next time. But those are the two options, the ground state, which you just described, how to get to the excited state, which we'll talk about another time. Those two options are like the 0 and 1 from classical computing. Those are the qubits associated to the electron. So I wanted to be precise because...
No, thank you. Yeah.
That's good, right? Okay.
Yeah, that's great. That's perfect. That's a great explanation.
Okay, but there's something else though that I think is really interesting. And this takes us back to this beautiful music analogy that we keep talking about. I'm so glad you brought your ukulele out and showed us this picture of a standing wave, because it turns out, okay, imagine last time you showed us this nice picture of this chip from IonQ, their trapped ion quantum computing chip. And we saw this line, like this nice pearl necklace of ions. So it's like this linear chain of ions. So it turns out, Adam, that in addition to initializing the internal state of each individual ion, there's another initialization step that you want to do, okay? It turns out that under the right conditions and when you set everything up the right way, and when you sort of cool these ions down to a certain level, meaning you reduce their energy enough, certain quantum effects take place. What's this effect that I'm referring to? Well, you can imagine if I have a whole bunch of ions and I just kind of pluck one or move one, you can imagine it's jiggling, right? And nobody else is paying attention to that. But if you set things up the right way, it turns out that if you kind of, pluck one, then the whole chain recoils together. And kind of like the wave, the jump rope that you were describing, or the standing wave of your ukulele string, there are certain vibrational modes or certain shapes that the string can take on. The same thing happens in this sort of quantum phenomena of having ions in a chain if you set them up the right way, if you cool them the right way. So it turns out they recoil together, and the shape of their recoiling only, there are certain options or certain shapes, and they're discrete. Like you can look like this shape or this shape or this shape, and you can enumerate them. This is totally analogous to how your electron can only occupy discrete energy levels. Analogously, the shape of the vibration of this single chain as a unit can only occupy certain shapes, so to speak. And so those vibrational modes, they're called phonons. Phonons, so like a unit of vibration versus photon, which is like a unit of light. So think of, this is how sound works, like the air molecules are vibrating and hitting my eardrum. And so it turns out that just like you're using lasers to want to sort of encourage that ion to relax to the ground state, you can also use lasers to slow the motion or the kinetic energy of these ions so that this quantum effect takes place and so that the chain sort of recoils together as a unit. So you mentioned optical pumping for initializing the state of the qubit in terms of energy. The process for initializing the vibrational mode of the whole chain is a process called Doppler cooling. So it's kind of related to the Doppler effect. In a nutshell, I like to think of it as like photons not only convey energy, but they also have momentum. So you can imagine if I'm an if I'm an atom and I'm moving this way, and here's a laser with a photon, and I'm moving and I hit something with momentum, that's going to slow my motion down. So that's kind of the idea without going into any detail whatsoever. So that's how you can use lasers to reduce the kinetic energy of these things. And under the right conditions, you get this nice, sort of, I think it's called a quantum harmonic oscillator. So it's like oscillating like your string on your instrument, but it's the quantum version of that. That's important to mention because it's going to come in to play next time when we talk about, okay, now we've got these qubits in the zero state, both in terms of energy and motion, but now what? Like, who cares? Why did we just spend however many minutes talking about all of this? Because just like you said, when you punch out your calculator, now you can do stuff. But you have to know, what equation or formula are you going to punch in? So that's what we're going to talk about next time. What equation or formula or algorithm do you now do? And how can you sort of manipulate the motion of the atoms together with their energy levels to do a useful computation? So I guess I just hinted at, quantum gates. That's what these are called. It turns out to involve more lasers. This is how you manipulate things. But I wanted to sneak that in there. It may sound, like super technical and like, wow, we're getting into the weeds, but it's fundamental, absolutely fundamental to creating entanglement, to talking about superposition, and these are like the bread and butter of quantum algorithms. So we'll get to them next time. But Adam, I know you've been talking about trapped ions for a while, but I like how you also can connect things back to superconducting quantum computers, which maybe folks are more familiar with. Do you have insights for this initialization into fiducial states in the superconducting world?
Yeah, I can try to add a little bit there. And yeah, this is with the trapped ions, pretty complicated. Like, it feels complicated. There's a bunch of different dimensions going on here with the harmonics, with different orbitals and discrete energies, and using lasers to do all sorts of things. With a superconducting quantum computer, to get that into its fiducial state, you just wait. That's it. So that's yeah, that's a major advantage. Once you have everything super cooled and set up in a superconducting quantum computer, if you just wait and instead of shooting with lasers in a superconducting quantum computer, you usually use microwaves. But if you just stop with the microwaves and kind of let everything settle down, just on its own, those qubits, those artificial atoms, will settle into their fiducial ground state. There's not, as far as I know, there aren't any other little tricks that you need to do with optical pumping. There's no harmonics that you need to make sure are in sync. These just settle down on their own into their ground state, waiting for you to then shoot them with microwaves to get them into their excited state. So it's a different system, and you can see how that's a definite advantage. There are other advantages and also some disadvantages when looking at superconducting quantum computers versus ion trap or other types of quantum computers. This is one place where superconducting quantum computers really shine, in that it's much easier to get them into their initialized or fiducial state.
Okay, interesting. I'm going to need to read up about that because I do not know much about how that works. Maybe we'll talk about that another time. Okay, this was great. I like how we sort of started with a theoretical idea of a qubit in our previous season of this episode, and now we've actually talked about what does that actually mean, putting it in the zero state. And I'm excited
for next time. Yeah, you were talking about algorithms, and now we're going to be talking about these algorithms that seem very theoretical, but we're actually talking about the implication of what happens when you take that algorithm and transform it into pulses of lasers aimed at ions within an actual computer. So again, this theme of just trying to move away from the theory itself, still need to talk about what that theory is, but into actual application and what happens when you're looking at some kind of quantum algorithm. How is that actually implemented in a situation like a trapped ion quantum computer? I'm really excited to talk more about that.
Yes, fantastic. We will do that next time.
Great. See you next time.